begun to sail the heavens. In those heavens, there are some worlds much like hell. Our planet is, in comparison, much like a heaven. But the gates of heaven and hell are adjacent and unmarked. The Earth is a lovely and more or less placid place. Things change, but slowly. You can lead a full life and never encounter anything in the way of a natural catastrophe more violent than a storm. And so we become complacent, relaxed, unconcerned. But in the history of the solar system, and even in human history, there are clear records of extraordinary and devastating catastrophes. We humans have now achieved the dubious distinction of being able to make our own major catastrophes, both intentional and inadvertent. On the landscapes of other planets, where the records of the past are better preserved, there is abundant evidence of major catastrophes. It's all a matter of timescale. An event which is improbable in 100 years may be inevitable in 100 million. But even on the Earth, in this century, there have been bizarre natural events. In remote central Siberia, there was a time when the Tunguska people told strange tales of a giant fireball that split the sky and shook the earth. They told of a blast of searing wind that knocked down people and whole forests. It happened, they said, on a summer's morning in the year 1908. In the late 1920s, L.A. Kulik, a Soviet scientist, organized expeditions to try and solve the mystery. He built boats to penetrate this trackless land, snowbound in winter, a swampy morass in summer. Eyewitnesses told of a ball of flame larger than the sun that had blazed across the sky 20 years before. Kulik assumed a giant meteorite had struck the Earth. He expected to find an enormous impact crater and rare meteorite fragments chipped off some distant asteroid. However, at ground zero, Kulik found upright trees stripped of their branches, but not a trace of the meteorite or its impact crater. He was deeply puzzled, but he thought perhaps there were meteorite fragments buried in the swampy ground. So he set about digging trenches and pumping out the water, but the expected meteoritic rock and iron was nowhere to be found. Undaunted, Kulik went on to make a thorough survey, despite the swarms of insects and other hardships, because he had discovered something that, in his own words, exceeded all the tales of the eyewitnesses and my wildest expectations. For more than 20 kilometers in every direction from ground zero, the trees were flattened radially outward like broken matchsticks. There must have been a powerful explosion several kilometers above the ground. The pressure wave spreading out at the speed of sound has been reconstructed from barometric records at weather stations across Siberia, through Russia, and on into Western Europe. Dust from the explosion reflected so much sunlight back to Earth that people could read by it at night in London, 10,000 kilometers away. This really remarkable occurrence is called the Tunguska event. But what was it? Well, perhaps, some scientists have suggested, it was a chunk of antimatter from space, annihilated on contact with the ordinary matter of the Earth, disappearing in a flash of gamma rays. But the radioactivity that you'd expect from matter-antimatter annihilation is to be found nowhere at the impact site. Or perhaps, other scientists have suggested, it was a mini black hole from space which impacted the Earth in Siberia, tunneled its way through the solid body of our planet, and plunged out the other side. But the records of atmospheric shock waves give not a hint of something booming out of the North Atlantic later that day. Or maybe, other people have speculated, it was a spaceship of some unimaginably advanced extraterrestrial civilization in desperate mechanical trouble, crashing in a remote region of an obscure planet. Well, if so, it's pretty startling that at the impact site there's not a piece, not the tiniest transistor of a crashed spacecraft. More prosaically, perhaps it was a large meteorite or small asteroid which hit the Earth. But even here, there are no observable telltale rocky or metallic fragments of the sort that you'd expect from such an impact. The key point of the Tunguska event is that there was a tremendous explosion, a great shock wave, many trees burned, an enormous forest fire, and yet no crater in the ground. There seems to be only one explanation which is consistent with all these facts, and that explanation is this. In 1908, a piece of a comet hit the Earth. No one saw it approach, a small point of light lost in the glare of the morning sun. It had been drifting for centuries through the inner solar system, like an iceberg in the ocean of interplanetary space. But this time, by accident, there was a planet in the way. From the time and direction of its approach, the object that hit the Earth seems to have been a fragment of a comet named NK, hurtling at more than 100,000 kilometers an hour. It was a mountain of ice about the size of a football field and weighing almost 1,000,000 tons. There was no warning until it plunged into the atmosphere. If such an explosion happened today, it might be thought, especially in the panic of the moment, to be produced by a nuclear weapon. Such a cometary impact and fireball simulates all the effects of a 15-megaton nuclear burst, including the mushroom cloud, with one exception: there would be no radiation. So, could a rare but natural event, the impact of a comet with the Earth, trigger a nuclear war? It's a strange scenario. A small comet hits the Earth, as millions of them have during the history of our planet, and the response of our civilization is promptly to self-destruct. Maybe it's unlikely, but it might be a good idea to understand comets and collisions and catastrophes a little bit better than we do. Now, a comet, at least as far as we understand them today, is made mostly of ice, water ice, maybe some ammonia ice, a little bit of methane ice. So in striking the Earth's atmosphere, a modest cometary fragment will produce a great radiant fireball and a mighty blast wave. It'll burn trees and level forests and make a sound heard around the world, but it need not make a crater in the ground. Why? Because the ices in the comet are all melted in the impact, and there's going to be very few recognizable pieces of comet left on the ground. We humans like to think of the heavens as stable, serene, unchanging. But comets suddenly appear and hang ominously in the sky night after night for weeks. So the idea developed that the comet had to be there for a reason. And the reason was that comets were kind of predictions of disaster, that they foretold the deaths of princes and the fall of kingdoms. In 1066, for example, the Normans witnessed an apparition or appearance of Halley's comet. Since a comet must, they thought, predict the fall of some kingdom, they promptly went ahead and invaded England. Here's King Harold of England looking a little glum. The events were noted in the Bayeux Tapestry, a kind of newspaper of the day. Or in the early 13th century, Giotto, one of the founders of modern realistic painting, witnessed another apparition of Comet Halley and inserted it into a nativity he was painting, a harbinger of a different sort of change of kingdoms. Around 1517, another great comet appeared. This time was seen in Mexico, and the Aztec emperor Moctezuma, maybe this is he, promptly executed his astrologers. Why? Well, they hadn't predicted the comet, and they sure hadn't explained it. Moctezuma was positive that the comet foretold some dreadful disaster. He became distant and gloomy, and in that way helped to set the stage for the successful Spanish conquest of Mexico under Cortez. In many cases, a superstitious belief in comets becomes a self-fulfilling prophecy. Here are two quite different representations of the great comet of 1577. This one pictured by the Turks, and this one by the Germans. In 1705, Edmund Halley finally figured out that the same spectacular comet was booming by the Earth every 76 years like clockwork. That comet is now called, appropriately, Comet Halley, and it's the same one that we talked about a moment ago, the comet of 1066. At that point, the subject began to lose a little of its burden of superstition, but hardly all. Public fear of comets survived, and, well, for example, look at this terribly nasty comet of 1857 that some people figured would splinter the Earth. By 1910, Halley's comet returned once more. But this time, astronomers using a new tool, the spectroscope, had discovered cyanogen gas in the tail of a comet. Now, cyanogen is a poison. The Earth was to pass through this poisonous tail. The fact that the gas was astonishingly, fabulously thin reassured almost nobody. So, for example, take a look at the headlines in the Los Angeles Examiner for May 9th, 1910. Say, has that comet cyanogened you yet? Entire human race due for free gaseous bath. Expect hijinks. Or take this from the San Francisco Chronicle, May 15th, 1910. Comet comes and husband reforms. Comet parties now fad in New York. Amazing stuff. In 1910, people were holding comet parties, not so much to celebrate the end of the world as to make merry before it happened. There were entrepreneurs who were hawking comet pills. I think I'm going to take one for later. And there were those who were selling gas masks to protect against the cyanogen. And comet nuttiness didn't stop in 1910. Long before 1066, humans marveled at comets. Our generation is beginning to understand them. Mercury, Venus, Earth, and Mars are small planets made mostly of rock and iron. Farther out, where it's colder, are the giant planets made mostly of gas. But comets originate from a great cloud beyond the planets, almost halfway to the nearest star. Occasionally, one falls in, accelerated by the sun's gravity. Because it's made mostly of ice, a comet begins to evaporate as it approaches the sun. The vapor is blown back by the solar wind, forming the cometary tail. Then it's flung back into outer darkness, its orbit so large
that have not returned for millions of years. These are the long-period comets, and for everyone plunging close enough to the sun to be discovered, there may be a billion others slowly drifting beyond Pluto's orbit. Very rarely, a long-period comet is captured in the inner solar system, becoming a short-period comet. It passes near a major planet like Saturn. The planet provides a small gravitational tug, enough to deflect it into a much smaller orbit. Although few comets are captured this way, those that are become well known because they all return in relatively short intervals. Once trapped in the inner solar system, among the planets, the chances of another near collision are increased. Here, a second encounter with Saturn further reduces the comet's orbital period to decades. A comet may take 10,000 years between close planetary encounters, but in this computer study, we've sped things up. A third encounter, this time with Jupiter, further reduces the comet's orbital period. Now, the comet must approach the sun and grow a tail every few years. Since the dust and gas in the tail are lost forever to space, the comet must slowly be eroding. Pieces of it break off. Sometimes, as we've seen, they even strike the Earth. In a few thousand years, if a short-period comet hasn't hit a planet, it will have evaporated away almost entirely, leaving sand-sized fragments which become meteors, and its core, which perhaps becomes an asteroid. Suppose I were a pretty typical comet, then what you would see would be a kind of tumbling snowball, spending most of my time out here in the outer solar system. I'd be a kilometer across. I'd be living most of my days in the gloom beyond Saturn, orbiting the sun. But about once every century, I would find myself careening inward, faster and faster, towards the inner solar system. By the time I would cross the orbit of Jupiter on my way to the orbit of Mars, I'd be heating up because I'd be getting closer to the sun. I'd be evaporating a little bit, and small pieces of dust and ice would be blown behind me by the solar wind, forming an incipient cometary tail. On the scale of such a solar system model, me, a cometary nucleus, would be smaller than a snowflake. Although, when fully developed, my tail would be longer than the spacing between the worlds. Now, sooner or later, comets on these long elliptical trajectories around the sun must collide with planets. The Earth and the Moon must have been bombarded by comets and asteroids, the debris from the early history of the solar system. In interplanetary space, there are many more small objects than large objects, so there must be, on a given planetary surface, many more impacts of small objects than of large objects. So a thing like the Tunguska impact happens on the Earth maybe every 1,000 years, but the impact of a giant cometary nucleus like Halley's Comet, let's say, happens only every billion years or so. Now, is there evidence of past collisions? When a large comet or a large rocky asteroid hits a planet, it makes a bowl-shaped crater. The few well-preserved impact craters on Earth were all formed fairly recently. The older ones have been softened, filled in, or rubbed out by running water and mountain building. Impacts make craters on other worlds, and about as often. But when the air is thin, when water rarely flows, when mountain building is feeble, the ancient craters are retained. This is the case on the Moon and Mercury and Mars, our neighboring terrestrial planets. They huddle around the sun, their source of heat and light, a little bit like campers around a fire. All of them are about 4.5 billion years old, and all bear witness to an age long gone of major collisions which do not happen at that scale and frequency anymore. If we move out past the terrestrial planets, beyond Mars, we find ourselves in a different regime of the solar system, in the realm of Jupiter and the other giant or Jovian planets. These are great worlds composed largely of the gases hydrogen and helium, some other stuff too. When we look at the surface, we do not see a solid surface, but only an occasional patch of atmosphere and a complex array of multicolored clouds. These are serious planets, not fragmentary little worldlets like the Earth. In fact, 1,000 Earths would fit in the volume of Jupiter. If a comet or asteroid were to accidentally impact Jupiter, it would be very unlikely to leave a crater. It might make a momentary hole in the clouds, but that's it. Nevertheless, we know that the outer solar system has been subject to a many billion-year history of impact cratering. Jupiter's moon Callisto is studded with thousands of craters, clear evidence of ancient collisions beyond Mars. And there are craters on other moons of Jupiter. Most of the thousands of large craters on our own moon were excavated billions of years ago. But were any recorded in historical times, the odds against it are about 1,000 to 1. Nevertheless, there's a possible eyewitness account of just such an event. It was the Sunday before the feast of St. John the Baptist, in the summer of 1178. The monks of Canterbury Cathedral had just completed their evening prayers and were about to retire for the night. The scholarly brother Gervais returned to his cell to read, while some of the others went outside to enjoy the gentle June air. In the midst of their recreation, they chanced to witness an astonishing sight, a violent explosion on the moon. This was a time when the heavens were thought to be changeless. The moon, the stars, and the planets were deemed pure because they followed an unvarying celestial routine. They were expected to behave without unseemly disruptions, like monks in a monastery. Was it wise to discuss such a vision? In every time and culture, there are pressures to conform to the prevailing prejudices. But there are also, in every place and epoch, those who value the truth, who record the evidence faithfully. Future generations are in their debt. A fire on the moon. Might it be some portent of ill fortune? Should the chronicler of the monastery be told? Was this event an apparition of the evil one? Gervais of Canterbury was a historian, considered today a reliable reporter of the political and cultural events of his time. This is his account of the eyewitness testimony he was given. Now there was a bright new moon, and as usual in that phase, its horns were tilted toward the east. And suddenly, the upper horn split in two. From the midpoint of this division, a flaming torch sprang up, spewing out over a considerable distance fire, hot coals, and sparks. After these transformations, Gervais continued, the moon from horn to horn, that is, along its whole length, took on a blackish appearance. Gervais took depositions from all the eyewitnesses. He later wrote, the present writer was given this report by men who saw it with their own eyes, and are prepared to stake their honor on an oath that they have made no addition or falsification. Gervais committed the account to paper, enabling astronomers 8 centuries later to try and reconstruct what really happened. It may be that 200 years before Chaucer, 5 monks saw an event more wonderful than many another celebrated Canterbury tale.
If a small drifting mountain were to hit the moon, it would set our satellite swinging like a bell. Eventually, the tremors would die down, but not in a mere 800 years. So is the moon still quivering from that impact? The Apollo astronauts emplaced arrays of special mirrors on the moon. Reflectors made by French scientists were also put on the moon by the Soviet Lunokhod vehicles. When a laser beam from Earth strikes one of these mirrors and bounces back, the round-trip travel time can be measured. At the McDonald Observatory of the University of Texas, a laser beam is prepared for firing at the reflectors on the moon, 380,000 kilometers away. By multiplying the travel time by the speed of light, the distance to that spot on the moon can be determined to a precision of 7 to 10 centimeters, the width of a hand. When such measurements are repeated over a period of years, even an extremely slight wobble in the moon's motion can be determined. The accuracy is phenomenal. The error is much less than 1/1,000,000th of a percent. The moon, it turns out, is gently swinging like a bell, just as if it had been hit by an asteroid less than 1,000 years ago. So there may be physical evidence in the age of spaceflight for the account of the Canterbury monks in the 12th century. If 800 years ago a big asteroid hit the moon, the crater should be prominent today, still surrounded by bright rays, thin streamers of dust spewed out by the impact. In billions of years, lunar rays are eroded, but not in hundreds. And there is a recent ray crater called Giordano Bruno in exactly the region of the moon where an explosion was reported in 1178. The entire evolution of the moon is a story of catastrophes. 4.5 billion years ago, the moon was accreting from interplanetary boulders, and craters were forming all over its surface. The energy so released helped melt the crust. After most of this debris was swept up by the moon, the surface cooled. But about 3.9 billion years ago, a great asteroid impacted. It generated an expanding shockwave and remelted some of the surface. The resulting basin was then flooded, probably by dark lava, producing one of the dry seas on the moon. More recent impacts excavated craters with bright rays named after Eratosthenes and Copernicus. The familiar features of the man in the moon are a chronicle of ancient impacts. Most of the original asteroids were swept up in the making of the moon and planets. Many still orbit the sun in the asteroid belt. Some, themselves almost fractured by gravity tides and by impacts with other asteroids, have been captured by planets, Phobos around Mars, for example, or a close moon of Jupiter called Amalthea. Somewhat similar to the asteroid belt are the rings of Saturn, composed of millions of small, tumbling, icy moonlets. Maybe the rings of Saturn are a moon which was prevented from forming by the tides of Saturn, or maybe it's the remains of a moon that wandered too close and was torn apart by the tides of Saturn. It's certainly a lovely place. Jupiter also has a newly discovered ring system which is invisible from the Earth. Now, there is a curious argument alleging major recent collisions in the solar system proposed by a psychiatrist named Immanuel Velikovsky in 1950. He suggested that an object of planetary mass, which he called a comet, was somehow produced in the Jupiter system. He doesn't say exactly how it's produced, but maybe it's spat out of Jupiter. Anyway, however it was made, some 3,500 years ago, he imagines, it made repeated close encounters with Mars, with the Earth-Moon system, having as entertaining biblical consequences the parting of the Red Sea so that Moses and the Israelites could safely avoid the host of Pharaoh, and the stopping of the Earth's rotation at the moment that Joshua commanded the sun to stand still in Gibeon. He also imagined that there was extensive flooding and volcanoes all over the Earth at that time. Well, then after a very complicated game of interplanetary billiards is completed, Velikovsky proposed that this comet entered into a stable, almost perfectly circular orbit, becoming the planet Venus, which he claimed never existed until then. Now, these ideas are almost certainly wrong. There's no objection in planetary astronomy to collisions. We've seen collision fragments and evidence throughout the solar system. The problem is with recent and major collisions. In any scale model of the solar system like this, it's impossible to have both the sizes of the planets and the sizes of their orbits to the same scale, because then the planets would be too small to see. If the planets were really to scale in such a model as grains of dust, it would then be entirely clear that a comet entering the inner solar system would have a negligible chance of colliding with a planet in only a few thousand years. Moreover, Venus is a rocky and metallic hydrogen-poor world, whereas Jupiter, the place that Velikovsky imagines it comes from, is made of almost nothing but hydrogen. There's no energy source in Jupiter to eject planets or comets. If one did enter the inner solar system, there is no way it could stop the Earth from rotating, and if it could, there's no way the Earth could start up rotating again at anything like 24 hours a day. There's no geological evidence for flooding and volcanism 3,500 years ago. Babylonian astronomers observed Venus in its present stable orbit before Velikovsky said it existed, and so on. There are many hypotheses in science which are wrong. That's perfectly all right. It's the aperture to finding out what's right. Science is a self-correcting process. To be accepted, new ideas must survive the most rigorous standards of evidence and scrutiny. The worst aspect of the Velikovsky affair is not that many of his ideas were wrong or silly or in gross contradiction to the facts. Rather, the worst aspect is that some scientists attempted to suppress Velikovsky's ideas. The suppression of uncomfortable ideas may be common in religion or in politics, but it is not the path to knowledge, and there's no place for it in the endeavor of science. We do not know beforehand where fundamental insights will arise from about our mysterious and lovely solar system. And the history of our study of the solar system shows clearly that accepted and conventional ideas are often wrong, and that fundamental insights can arise from the most unexpected sources. We've evolved on the planet Earth, and so we find it a congenial place. But just next door is Venus, until recently enveloped in mystery. It has almost the same size and mass as the Earth. Might our sister world be a balmy summer planet, a little warmer than the Earth because it's a little closer to the sun? Are there craters, volcanoes, mountains, oceans, life? The first person to look at Venus through a telescope was Galileo in 1609. But all he could see was a featureless disk. And as optical telescopes got bigger, that's all anybody could see. A disk with no details on it at all. Venus evidently was covered with an opaque layer, thick clouds concealing the surface. For centuries, even the composition of the clouds of Venus was unknown. I mean, you could go outside, look up, see Venus with the naked eye, observe sunlight reflected from the clouds of Venus. What were you looking at? What were the clouds made of? Nobody knew. As a result, imagination ran riot. The absence of anything you could see on Venus led some scientists and others to deduce that the surface was a swamp. The argument, if we can dignify it with such a phrase, went something like this. I can't see a thing on the surface of Venus. Why not? Because it's covered with a dense layer of clouds. Well, what are clouds made of? Water, of course. Therefore, Venus must have an awful lot of water on it. Therefore, the surface must be wet. Well, if the surface is wet, it's probably a swamp. If there's a swamp, there's ferns. If there's ferns, maybe there's even dinosaurs. Observation, you couldn't see a thing. Conclusion, dinosaurs. Well, if just looking at Venus was so unproductive, what else could you do? The next clue came from early work with that, a glass prism. An intense beam of ordinary white light is made to pass through a narrow slit and then through the prism. The result is to spread the white light out into its constituent rainbow of colors. This rainbow pattern is called a spectrum. Think about it. White light enters the prism. What comes out of the prism is colored light. Lots of colors. Where did they come from? They must have been hiding in the white light. White light must be a mixture of many colors. Here we see the spectrum running from violet, blue, green, yellow, orange to red. Since we see these colors, we call this the spectrum of visible light. The sun emits lots of visible light. The air is transparent to it, so our eyes evolved to work in visible light. But there are many other frequencies of light which our eyes can't detect. Beyond the violet is the ultraviolet. It's just as real, but you need instruments to detect it. Beyond the ultraviolet are the X-rays and then the gamma rays. On the other side of visible light, beyond the red, is the infrared, again real, again invisible. Beyond the infrared are the radio waves. Now, this entire range from the gamma rays way over there to the radio waves all the way over here are simply different kinds of light. They differ only in the frequency. They're all useful, by the way, in astronomy. But because of limitations of our eyes, we have a prejudice, a bias, a chauvinism to this tiny rainbow band of visible light. Now, a spectrum can be used in a simple and elegant way to determine the chemical composition of the atmosphere of some distant planet or star. Different atoms and molecules absorb different frequencies or colors of light, and those absorbed or missing frequencies appear as black lines in the spectrum of the light we receive from the planet or star. Each and every substance has a characteristic fingerprint, a spectral signature, which permits it to be detected over a great distance. As a result, the gases in the atmosphere of Venus at a distance of 60 million kilometers have been determined, their composition has been determined from the Earth. It's amazing to me still. We can tell what a thing is made out of at an enormous distance away without ever touching it. Our eyes can't see in the near-infrared part of the spectrum, but our instruments can. Here's the absorption pattern of lots and lots of carbon dioxide, dark lines in characteristic patterns at specific frequencies. You'd detect a different set of infrared lines if, say, water vapor were present. If Venus were really soaking wet, then you should be able to determine that by finding the pattern of water vapor in its atmosphere. But around 1920, when this experiment was first performed, it was found that the Venus atmosphere seemed to have not a hint, not a smidgen, not a trace of water vapor above the clouds. And so instead of a swampy, soaking wet surface, it was suggested that Venus was bone dry, a desert planet with clouds composed of fine silicate dust. But later, spectroscopic observations revealed the characteristic absorption lines of an enormous amount of carbon dioxide. So some scientists thought there must be lots of carbon compounds on the surface, making this a planet covered with petroleum. Others agreed that the atmosphere was dry, but thought the surface was wet. With all that CO2, it had to be carbonated water. Venus, they thought, was covered with a vast ocean of seltzer. Now, the first hint of the true situation on Venus came not from the visible or the ultraviolet or the infrared part of the spectrum, but from over here
in the radio region. We're used to the idea of radio signals from intelligent life, or at least semi-intelligent life, radio and television stations. But there are all kinds of reasons why natural objects should emit radio waves. One reason is that they're hot. And when, in 1956, Venus was for the first time observed by a radio telescope, the planet was discovered to be emitting radio waves as if it were at an extremely high temperature. But the real demonstration that the surface of Venus was astonishingly hot came when the first spacecraft penetrated the obscuring clouds of Venus and slowly settled on the surface of the nearest planet. These were the unmanned spacecraft of the Soviet Venera series. In our spaceship of the imagination, we retrace their course. From a distance, our sister planet seems serene and peaceful, its clouds motionless. These clouds are near the top of a great ocean of air, about 100 kilometers thick, composed mainly of carbon dioxide. There's some nitrogen, a little water vapor and other gases, but only the merest trace of hydrocarbon. And the clouds turn out to be not water, but a concentrated solution of sulfuric acid. Even in the high clouds, Venus is a thoroughly nasty place. The clouds are stained yellow by sulfur. There are great lightning storms. As we descend, there are increasing amounts of the noxious gas sulfur dioxide. The pressures become so high that early Venera spacecraft were crushed like old tin cans by the weight of the surrounding atmosphere. Beneath the clouds, in the dense, clear air, it's about as bright as on an overcast day on Earth. But the atmosphere is so thick that the ground seems to ripple, distort. The atmospheric pressure down here is 90 times that on Earth. The temperature is 380 degrees centigrade, 900 Fahrenheit, hotter than the hottest household oven. This is a world marked by searing heat, crushing pressures, sulfurous gases, and a desolate, reddish landscape. Far from the balmy paradise imagined by some early scientists, Venus is the one place in the solar system most like hell. But today, as in ancient tradition, there are travelers who will dare a visit to the underworld. Venera 9 was the first spacecraft in human history to return a photograph from the surface of Venus. It found the rocks curiously eroded, perhaps by the corrosive gases, perhaps because the temperature is so high that the rocks are partly molten and sluggishly flow. The Soviet Venera spacecraft, their electronics long ago fried, are slowly corroding on the surface of Venus. They are the first spaceships from Earth ever to land on another planet. The reason Venus is like hell seems to be what's called the greenhouse effect. Ordinary visible sunlight penetrates the clouds and heats the surface, but the dense atmosphere blankets the surface and prevents it from cooling off to space. An atmosphere 90 times as dense as ours, made of carbon dioxide, water vapor, and other gases, lets in visible light from the sun, but will not let out the infrared light radiated by the surface. So the temperature rises until the infrared radiation trickling out to space just balances the sunlight reaching the surface. The greenhouse effect can make an Earth-like world into a planetary inferno. In this cauldron, there's not likely to be anything alive, even creatures very different from us. Organic and other conceivable biological molecules would simply fall to pieces.
The hell of Venus is in stark contrast with the comparative heaven of its neighboring world, our little planetary home, the Earth. Here, the atmosphere is 90 times thinner. Here, the carbon dioxide and water vapor make a modest greenhouse effect, which heats the ground above the freezing point of water. Without it, our oceans would be frozen solid. A little greenhouse effect is a good thing. But Venus is an ominous reminder that on a world rather like the Earth, things can go wrong. There is no guarantee that our planet will always be so hospitable. To maintain this clement world, we must understand it and appreciate it. The Earth is a place to our eyes more beautiful than any other that we know. But this beauty has been sculpted by change. Gentle, almost indetectable change, and sudden, violent change. In the cosmos, there is no refuge from change. The Sphinx, human head, lion's body, constructed more than 5,500 years ago. That face was once crisp and cleanly rendered, like this paw I'm standing on. The paw has been buried in the sand until recently and protected from erosion. The face is now muddled and softened because of thousands of years of sandblasting in the desert and a little rainfall. In New York City, there is an obelisk called Cleopatra's Needle. It comes from Egypt. In only a little more than a century in New York Central Park, the inscriptions on that obelisk have been almost totally obliterated, not by sand and water, but by smog and industrial pollution, a little bit like the atmosphere of Venus. Slow erosion wipes out information. On the Earth, mountain ranges are destroyed by erosion in maybe tens of millions of years, small impact craters in maybe hundreds of thousands of years, and the greatest artifacts of human beings in thousands or tens of thousands of years. In addition to such slow and uniform processes, there are rare but sudden catastrophes. The Sphinx is missing a nose. In an act of idle desecration, some soldiers once shot it off. If you wait long enough, everything changes. Slow, uniform processes, unheralded events, the sting of a sand grain, the fall of a drop of water, can over the ages totally rework the landscape. And rare, violent processes, exceptional events that will not recur in a lifetime, also make major changes. Both the insignificant and the extraordinary are the architects of the natural world. The destruction of trees and grasslands makes the surface of the Earth brighter. It reflects more sunlight back to space and cools our planet. After we discovered fire, we began to incinerate forests intentionally to clear the land by a process called slash and burn agriculture. And today, forests and grasslands are being destroyed frivolously, carelessly, by humans who are heedless of the beauty of our cousins, the trees, and ignorant of the possible climatic catastrophes which large-scale burning of forests may bring. The indiscriminate destruction of vegetation may alter the global climate in ways that no scientist can yet predict. It has already deadened large patches of the Earth's life-supporting skin. And yet we ravage the Earth at an accelerated pace, as if it belonged to this one generation, as if it were ours to do with as we please. The Earth has mechanisms to cleanse itself, to neutralize the toxic substances in its system. But these mechanisms work only up to a point. Beyond some critical threshold, they break down. The damage becomes irreversible. Our generation must choose. Which do we value more? Short-term profits or the long-term habitability of our planetary home? The world is divided politically, but ecologically it is tightly interwoven. There are no useless threads in the fabric of the ecosystem. If you cut any one of them, you will unravel many others. We have uncovered other worlds with choking atmospheres and deadly surfaces. Shall we then recreate these hells on Earth? We have encountered desolate moons and barren asteroids. Shall we then scar and crater this blue-green world in their likeness? Natural catastrophes are rare, but they come often enough. We need not force the hand of nature. If we ruin the Earth, there is no place else to go. This is not a disposable world, and we are not yet able to re-engineer other planets. The cruelest desert on Earth is far more hospitable than any place on Mars. The bright sandy surface and dusty atmosphere of Mars reflect enough sunlight back to space to cool the planet, freezing out all its water, locking it in a perpetual ice age. Human activities brighten our landscape and our atmosphere. Might this ultimately make an ice age here? At the same time, we are releasing vast quantities of carbon dioxide, increasing the greenhouse effect. The Earth need not resemble Venus very closely for it to become barren and lifeless. It may not take much to destabilize the Earth's climate, to convert this heaven, our only home in the cosmos, into a kind of hell. The The study of the global climate, the sun's influence, the comparison of the Earth with other worlds, these are subjects in their earliest stages of development. They are funded poorly and grudgingly. And meanwhile, we continue to load the Earth's atmosphere with materials about whose long-term influence we are almost entirely ignorant. There are worlds that began with as much apparent promise as Earth, but something went wrong. Knowing that worlds can die alerts us to our danger. If a visitor arrived from another world, what account would we give of our stewardship of the planet Earth? In the history of the solar system, have worlds ever been destroyed? Most of the moons in the outer solar system have craters on them made by cometary impacts. Some have such large craters, though, that if the impacting comets had been just a little bit bigger, the moons would have been shattered. What would the results of such a collision look like? Maybe a planetary ring. The idea has been growing that little worlds are every now and then demolished by a cometary impact. The fragments then slowly coalesce and a moon arises again from its own ashes. Some moons may have been destroyed and reconstituted many times. For our own world, the peril is more subtle. Since this series was first broadcast, the dangers of the increasing greenhouse effect have become much more clear. We burn fossil fuels like coal and gas and petroleum, putting more carbon dioxide into the atmosphere and thereby heating the Earth. The hellish conditions on Venus are a reminder that this is serious business. Computer models that successfully explain the climates of other planets predict the deaths of forests, parched croplands, the flooding of coastal cities, environmental refugees, widespread disasters in the next century, unless we change our ways. What do we have to do? 4 things. 1, much more efficient use of fossil fuels. Why not cars that get 70 miles a gallon instead of 25? 2, research and development on safe alternative energy sources, especially solar power. 3, reforestation on a grand scale. And 4, helping to bring the billion poorest people on the planet to self-sufficiency, which is the key step in curbing world population growth. Every one of these steps makes sense apart from greenhouse warming. Now, no one has proposed that the trouble with Venus is that there once was Venusians who drove fuel-inefficient cars, but our nearest neighbor, nevertheless, is a stark warning on the possible fate of an Earth-like world.